Take a look at this workshop. On the right, Sudarshan is holding a long rod of iron. He's been heating that solid block in his furnace until it's glowing red hot and ready to be worked. As he strikes the glowing iron with his heavy hammer, sparks fly across the room. He isn't just hitting it, he's using that force to carefully squash and shape the metal into a tool, like an axe. But imagine if he tried that with a different material. In this photograph, a miner is surrounded by jagged lumps of coal. If Sudarshan put one of those pieces of coal on his anvil and hit it with that same hammer, it wouldn't shape into anything. By watching how a material reacts to that hammer strike, whether it changes shape or simply falls apart, we can start to see which team it belongs to in the natural world. Iron and coal are just two examples of the fundamental ingredients that make up our world. Scientists call these ingredients elements, and they are the simplest substances that make up everything from the tools in this shop to the stars in the sky. This grid shows all 118 known elements. You can think of them as the master list of everything that exists in the universe. To make this long list easier to handle, we divide these elements into two main groups, based on how they behave: metals and nonmetals. Let's put some common materials to the test. On our workbench, we have pieces of copper and aluminum, an iron nail, a lump of coal, and some yellow sulfur. First, look at their surfaces. The copper, aluminum, and iron all have a natural, bright shine. This metallic luster is the first sign that they belong on the metal team. The coal and sulfur, however, are dull. They don't reflect light at all, which is common for nonmetals. Now the smash test. As you see here, we're going to hit this iron nail with a hammer. The nail doesn't break, it gets squashed flat. This ability to be hammered into sheets without shattering is why we describe metals as malleable. But look what happens to the coal or sulfur under that hammer. Instead of flattening out, they instantly crumble into jagged bits and dust. This test shows a clear divide. Metals are usually hard and malleable, while nonmetals are brittle and easily broken. You can even tell these teams apart with your ears. Think about the sound a metal coin or a spoon makes when it hits a hard floor. It creates a clear, ringing note that lasts for a second. That ringing quality is why we call metals sonorous. If you dropped a piece of wood or a lump of coal, you'd just hear a short, dull thud. Because metals ring when struck, they're the perfect choice for making things like school bells or the strings on a guitar. We can also test how these materials move energy. Imagine putting a metal spoon and a wooden spoon into a cup of hot water. After a few minutes, the handle of the metal spoon will be too hot to touch, but the wooden handle will still feel cool. This is because metal is a great conductor. It carries that heat quickly from the water to your hand. Wood is a poor conductor, so the heat stays trapped in the water. Metals also carry electricity just as easily, which is why the tools electricians use have handles made of plastic or rubber. Those nonmetals block the electricity and keep the person safe. We use these rules every day to build our world, picking metals when we want to move energy and nonmetals when we want to stop it. Finally, we can see how these teams react to the air around them. Think about an iron gate left out in the rain. Over time, the shiny metal reacts with oxygen in the air to form that familiar flaky brown rust. This reaction creates a new substance called a metal oxide. If we test that oxide with a special strip of red paper, it turns blue. This tells us that metal oxides are basic, which is a chemical category that includes things like soap or baking soda. Nonmetals do the opposite. When they react with oxygen, they create acidic oxides, the same chemical family as lemon juice or vinegar. This means these two teams aren't just different to the touch, they are chemically different at a level we can't even see. Now that you've seen these tests in action, you have a clear way to look at almost any material you find. On the metal side, we have elements that are shiny, can be squashed into shapes, ring when hit, and carry heat and electricity. On the nonmetal side, we have elements that are dull, crumble under a hammer, and block the flow of energy. We use these specific properties to build incredible things. This bridge stands because we use the strength and malleability of steel to create a massive structure that can hold its own weight. From the tools in a workshop to the bridges in our cities, we are constantly sorting and using elements based on these simple, reliable rules of nature.